I'm Dave Choffnes from Northeastern University. Today I'm going to talk about revealing and controlling personal information leaks on our mobile systems. This is joint work with the lead grad student, Jingjing Ren, and a bunch of other collaborators, Ashwin Rao, Martina Lindorfer, and Arnaud Legou, without whom we would not be able to do this project. So the motivation for this work is really these things. If you're like me, Heather West, you're beholden to these devices. They have all kinds of great functionality. They're always connected to the internet. They let us do things like, important things like play Candy Crush or check Facebook feeds or Twitter feeds. Other actually important things like check our bank account balances. And implicitly, we're trusting these devices to handle some really sensitive information. They're figuring out who we are, who our friends are, and they're storing sensitive information like our usernames and passwords. So the question that we had in this work is, what kind of personal information are these devices transmitting out into the network? Where are they going? And is there anything that we can do to help users control this? So to start answering this question, we did a controlled study where we manually interacted with the top 100 apps from every app store, well, the ones that mattered. So the Apple App Store, Google Play, and Windows Phone. And we tried to understand the fraction of them that are leaking information of different categories. So on the y-axis is the fraction. On the x-axis here is the personal information leak types, coarsely categorized. And what immediately pops out of this is that there's some basic run-of-the-mill tracking going on, things that maybe you're not surprised about, but maybe you didn't know just how much was happening. So unique identifiers, on average, about half the apps in the top 100 are using these to track individuals, and even a significant fraction of apps are sending out your locations. So this is, like I said, run-of-the-mill tracking, maybe not terribly surprising, but the thing that also was disturbing is we saw lots of very personal information being leaked. So this includes user identifiers like your email address or your gender, and also credentials, usernames and passwords being sent out. So one of the key takeaways from this figure is that information leaks are pervasive from these mobile devices. So given this is the case, we wanted to investigate ways to have some control over it. Of course, this is not a new problem. There's been lots of research in this area. One approach is to simply make the operating system take care of it. So if the operating system, after all, it knows where what your contacts are, it knows what your location is, why don't you just make sure that the operating system prevents that stuff from ever hitting the network in the first place? So there's tools that do this. Information flow analysis is a popular technique. But in general, what we find is that these aren't things that average users can deploy on their systems. They have to root their OS. Usually the performance is terrible. So instead, there's another technique you could use, which is just rely on the fact that if information is leaking, it's leaking over the network. So actually look at the network traffic itself and detect and stop the leaks there. What's nice about this approach is it's no longer dependent on any particular OS or app store. And in fact, this is kind of a trivial problem if you think about it. If you know what the information is that's leaking, all you have to do is a text search under network traffic and find it. So it's trivial if you know what it is, but of course the problem is that for arbitrary users, we don't know what the personal information is. In fact, most users don't know things like what their unique identifiers are. So a problem that we're solving in this context is what you do, or how you solve this problem when you don't know users' PII in advance. So we built a system called Recon that does this. And our key hypothesis is that these PII leaks have distinguishing characteristics that we can use to extract them from network traffic. So one thing you might imagine is that it's just simple key value pairs. Like you look for user equals Recon, and there's some username right there. What we found if you try to use this approach is that it's not terribly accurate, and that's because there's ambiguity in many cases. So for example, ID equals, well, ID might be your user ID, ID might be your device identifier, or it could be an ephemeral session identifier that has nothing to do with you. So instead, what we want to do is actually learn the structure of information contained in network flows that are associated with PII leaks. So that's our approach. We use machine learning to do this. One of the nice things about using machine learning is that, again, we don't need to know what your personal information is in advance. We're not looking for your username or password. We're looking for features in network flows that predict that your username or password is about to be sent out. We can also use machine learning to adapt our system. So if these formats change over time, we just retrain and relearn. So Recon leverages this idea. We use machine learning to identify information leaks in network traffic. We use software middle boxes to actually intercept and control them if users want to modify what information is being sent. And because this approach just works on network traffic, we've been able to make it available today on all major platforms: iOS, Android, Windows Phone. In fact, I've been running this on my iPhone for the better part of a year. Okay, so before I go into any of the details, I want to talk a little bit about the interfaces that this provides to users. One is we show users what is being sent about them. So what you see on the right-hand side there is our web view into users' data. When you're connected to the system, you can see this interface. And in this particular case, in the red box are all of the types of information that have been sent out. You'll notice actually the first one is password. We have seen many cases of this. In fact, I've been victim of plain text passwords being sent out over the network. But here's a name being linked, someone's actual real name, not just their IP address. So in addition to showing users this kind of information, we also give them the ability to tell us if we're right or wrong. Because remember that we're inferring this. We don't necessarily have 100% accuracy. And so users can go in, you can see the red box on the left-hand side there, and tell us if we're right, if we're wrong. And we use that information to retrain the classifier, but they can also tell us things like they're not sure, because most users don't know what their IMEI is. Or they can say it's not about them. So that's one interface we provide. We also provide something that gives an aggregate view of the kind of tracking information that one of the audience members brought up, which is how your location is being tracked over time. This is an interface we call Where They Know You've Been. And every time your location leaks, we drop a pin. And that pin shows you which app sent it, to what destination, and when it happened. And we're hoping that this gives maybe just the right level of creepiness to users, that maybe they'll start caring about their privacy. So far I've painted a pretty depressing picture for users. I can tell them all of this information about them that's being sent over the network, how they're being tracked, but it kind of leaves them unsatisfied at that point. So we're not stopping there. We also give users the ability to control the information being sent out. So some strategies that we support today is simply blocking specific leaks that we've detected. So if you see, for example, that a password has been leaked in plain text and you don't want it to happen again, you can tell us. We can also modify the information. So for example, if you don't want an advertiser to be able to uniquely track you, maybe you can randomize that identifier. We can also coarsen locations, and other things that we're looking at are more advanced profiles and easy to use profiles so that users have better control over their privacy without having to understand absolutely everything about every piece of information being sent out. So maybe be able to pretend to be a user of a certain type when you use your mobile device, or hide among a set of K other users that are all using the same profile to provide some level of anonymity. Okay, so now that I've told you about how the system, or the interface the system provides to users, I'll tell you a little bit about how it works. Some of the key challenges that we have to address for machine learning, the first is, how are you going to do it in the first place? What technique are you going to use? So we tried them all, or at least everything we could get our hands on. And what we found is the decision tree gave us the best trade-off between performance, which is to say classifying or correctly inferring within a very short period of time, fractions of a millisecond, so users don't notice delay, and accuracy, so not showing them incorrect results and making sure that we cover most of the leaks. Now, of course, once you pick a classifier, you have to train it with some data. You have to give it some ground truth. So the way we got ground truth is that study I just talked about before. We spent lots of time interacting manually with apps using very conspicuous personal information so that we can easily extract it and label it. And then we also use the feedback from labels that users provide us, whether we're right or wrong. And this information can use to continuously train our classifiers. In terms of the nuts and bolts of it, what we do is we break up network flows into words. Those words are associated with leaks, and of course there's way too many words that come out of this analysis, so we do some feature selection, throwing out words that we know are not helpful for identifying leaks, and that makes our system train quickly. And then to evaluate how well we're doing, as I mentioned before, we do controlled experiments, but we also let the users tell us. Because in the end, whatever we learn in the lab may not necessarily be representative of what's happening in the real world, and we want to reflect that as well. Okay, so how do we do in the lab? Well, what we found is that we have 99% overall accuracy. Coming with that is a relatively low false positive and false negative rate. So most of the time when we show users information that's being leaked, we're right. And it's rarely the case that we miss information that's being leaked. If you wonder why there's no 1% or those numbers don't add up, the reason is because most of the flows don't actually leak information. So we're talking about the minority of cases when we talk about the false positive and false negative rates. The reason the system is accurate is we train our system not just over all data, but we actually segment it into the domain that's the destination of traffic. Because what we find is that if there's information being leaked to a certain domain, it's probably because some developer wrote something specific to that domain, but if you look at a different domain, it was a different developer. It was maybe a different tracker, and so they use a different format. And we keep those separate so our classifiers don't get confused by mixing all of these flows together. We also find that the decision tree is useful for identifying things beyond simple key value pairs. So just to give you an example of what I'm talking about, here's where you have to travel 4 nodes in terms of finding 4 different identifiers that are either present or not present in a flow before you actually find a leak. If you follow the red arrows and find positive, that's actually where there's an information leak. If any of the conditions change, you see that we have negative examples most of the time. So basically, the decision tree is able to learn this structure that I was talking about earlier. Okay, so beyond just our controlled experiments, we wanted to understand how this technique stands up to the other thing I talked about, information flow analysis, where you actually know, or the operating system knows what information is being leaked. And there's a bunch of different ways of doing this, static, dynamic, and hybrid. We looked at all of them, so FlowDroid, Andrubis, and App Audit. And on the y-axis here is the fraction of all leaks found across all of these approaches. And on the x-axis, again, we have the types of leaks. So blue is for Recon. And we were actually pretty surprised to find that Recon is finding significantly more PII than the information flow analysis solutions. So one thing I should mention here, there are certainly many cases where the other approaches find leaks that Recon missed. So we're not perfect. But what was really nice is when these tools produce network flows, we now have more labeled data to feed into our classifier. We missed them, but then we just retrain our classifier, and when we do that, we found that Recon successfully finds all of these leaks. So this is an approach that we are going to rely on going forward, is that we're not just getting information from our manual tests, not just from our users, but throw every available tool at this problem that we can find that's going to reliably identify leaks, and then train our system based on that. We also conducted a user study, so we let this go outside of the lab. There were more than 30 devices, and both iOS and Android. One thing that we wanted to know is, did users find this useful, and did they change their behaviors in response to the information we showed them? The majority did, in fact, do this. We also found significant cases of credentials being leaked in user traffic. A large fraction of them were actually verified by our users. As I said, I was one of the victims. We found on average, iOS was leaking more information per user than Android. Don't know why, it's just an interesting fact. And we found cases of suspicious leaks, things that maybe weren't against any particular privacy policy, but certainly violated our expectations of what an app would do. So for example, we found a recipe app was leaking location information. And we don't really know why it's doing that, because location is not critical to the operation of telling you how to cook a meal. We also saw video, game, and news apps leaking gender information. We found this was interesting because, of course, this isn't even stored on your phone. This is something that's been inferred about you by the advertisers. And we have lots more results. Obviously, this is a short talk, so if you're interested, please visit this website. You can find a tech report with more details. So at this point, I'm going to wrap up. So just to summarize, Recon is a tool that provides transparency and control over personal information leaks. The way the tool works is it just needs access to the network traffic coming from your phone, which is nice because it means that we can deploy it today. Anyone can use it. We use machine learning to automatically identify leaks. We use crowdsourced reinforcement to retrain and refine our classifiers. And it does work today. So if you're at all interested in this tool, I encourage you to visit our Recon website where you can sign up. And at this point, I will take any questions. Yeah, it does work.
Yes, thank you very much. Marcus Heider from the Center for Information Policy Leadership.
Mm-hmm.
In terms of your study and your research, was it at all relevant what use the leaked data is being put to? Does it matter whether it's being put to a good purpose or something that's envisioned by the app as part of the process? And leaked seems to be a loaded term. Does that cover all third-party sharing for purposes of your study and your work?
So I guess you're right. We use a loaded term with leak, although I still don't think that we're trying to impart a value judgment. It's just that we were able to see this information being sent by the devices, and it was sent over the network. So I think it's certainly relevant, but I think it's, I mean, in terms of our study, we didn't have that kind of information as to whether certain information was essential to the functionality of the app. And that's actually something that we're looking into, because if we're moving in this direction of allowing users to control or change or block information being sent out, well, if users are blocking their location to Google Maps, it's not going to be able to work. So there's obviously cases where sending information is absolutely critical to the functionality of the app. And then there's other cases where it's absolutely not essential at all. So we're trying to understand that as well. But for the purpose of this work, we didn't really concern ourselves whether it was second or third parties. These were all just leaks, and we just want users to be aware of the information, and the next step is trying to understand the implications of that information.
I think there were some, yes.
Yes.
What would you suggest rather than transmitting data, sharing with third parties, second parties? There could be a whole range of potentially beneficial purposes of data sharing that could be disclosed in the app, for example. And I just want to know how that's accounted for in this stuff, whether it matters. Yeah, okay. Whether there's good uses and bad uses, for example.
That's a fair point. It's certainly takes more words to put it in that context. And I don't know that sharing is always the right. But anyway, it's an interesting point.
Yes, Tom Candela, research pays, freelance writer. In terms of that recipe example, did it occur to you to actually phone up the company and ask them why they're using it? And in other words, just go to all these companies and ask them what they're doing and see if there's some kind of information. Will they even share that information? I think it'd be interesting.
I think that's a great point. We have not contacted them. I mean, so there's certain cases where, like, if a password is sent over plain text, it's clearly a security violation. And so we tell companies when we see these things and try to get them to fix it. For this other information, we haven't asked them yet. I would be surprised to get many responses, but it's certainly something that I think is worth asking.
Quick one. How do you deal with encrypted traffic?
Great question. Finally, we get to some of the backups. So thank you for asking that. So one thing I kind of danced around is that the way Recon works is it needs access to network traffic. I didn't specify. It needs to see plain text network traffic. We're not necessarily going to, the approach can't operate just on encrypted traffic. So if something is encrypted, you need some way to get access to plain text flows so that our system can operate on it. So one thing you could do is you could leverage existing approaches that were recently proposed, MCTLS or blind box, essentially allow middle boxes to peer into parts of traffic. That's one potential avenue. Another way to do it is some form of man-in-the-middling SSL connections. We do not do this, we don't propose doing this in an unconstrained way. If we're gonna do this, one thing that you could do is actually send it to a hardware device that you run in your own network. So we are thinking of a Raspberry Pi-based deployment of this. It's your hardware, your own network, so it seems like it's okay for you to man in the middle your own traffic. Or another approach is to actually use Haystack, so that's something that Narcio has been working on, and that in that case, the traffic never leaves the device, so you can man in the middle it on an Android device before it hits the network.
Okay, great question. Let's try to find the other backup site.
Quick one. Dave, do you have any plans about opening up the platform? It certainly takes a lot of work to train these classifiers, a lot of data, so it would make sense to somehow export the classifiers for other services that want to do something in the area so they don't have to reinvent the wheel.
Absolutely. So I think also I should mention any work on privacy I think needs to be done in the open. That means open access to source code, open access to data that doesn't contain user identifiers so that others can benefit from it. So we do believe that the classifiers themselves fit in that category. We think even in the model where users run their own sort of decentralized versions of Recon, that the information trained in those classifiers can be shared so that everyone can benefit from that. We still have some work to do to make sure that no side channel information is leaking about users when we share those classifiers, but I think that's absolutely critical. And of course, we can share the data from manual experiments. So when we manually interact with our devices or anyone else provides that information, I think that not just the classifiers, but the data they were trained on are really important to make available.
Okay, we take one more question.
Yeah. Hi, Nick Nikiforakis, Stony Brook. So I'm asking this because we've done some work in that area and we've been stumbling upon this issue all the time. So you said that you can man in the middle in some way, right? Mm-hmm. But that assumes that the application will rely on the network layer to do the encryption for it, mm-hmm. right? So the application, it seems to me that the application today could sort of just do its own encryption within the application, mm-hmm. Send a symmetric key randomly generated for every user, whatever, right? Mm-hmm. And so all of these techniques that essentially either grepping or machine learning on clear text traffic break.
Yeah.
Right. So do you have any thoughts about how to move forward?
So one way that I look at this problem is
You need the slide or not?
It's fine.
Okay.
So one way I'm looking at this problem is I think if there's a service that is sending information about users, they should probably use standard techniques to protect it. If they're, so like SSL. If they're doing their own encryption, that seems to me like they're hiding something. And I'm hoping that essentially instead of going to an environment where we have a cat and mouse game and these apps or trackers or whoever are just finding more and more ways to obfuscate or hide what they're doing, that the obfuscation and hiding itself indicates they're doing something that they don't want us to see. And that is something that can be made transparent to users and to policymakers and move away from that game where they keep hiding and move into an environment where things are more transparent.
Okay, so the solution to you is more of a policy solution.
I mean, yeah.
Identification of that something shady is happening and then a policy solution.
Yeah.